Today I want to, in video number 10 of our TEAS preparation, I want to talk about nomenclature. That is, how do you name compounds? Um, the modern system of naming compounds developed in the 18th century. We started feeling the uh, birth pains of modern science and chemistry in the 17th century, but it wasn't until the uh, 18th century before we got a system that was regular and accepted for naming compounds. Up to that point, the alchemical system was used, and it was all over the place. It used, well, actually, al- um, alchemical system was based upon the guild system that was common in Europe at the time, in which you had a master and you had maybe he had some uh, workers with him, journeymen, and he may have had one or two apprentices. And whatever was discovered was kept within that little group. There was no attempt to share information, no major attempt to share information among masters. They guarded their secrets jealously, and uh, their naming system was a reflection of that motivation. So they had things, they had common names for things. They had for chemicals, they had names for procedures. Um, some have filtered down through to modern times. For instance, water. Right, water. If we follow the etymology of water back to its roots, we find that water just means wet, right? But um, there are other uh, names that have filtered through, and we've accepted them as systematic names, although they're commonly used, such as ammonia. Right, ammonia is not a systematic name for for this molecule. A systematic name would be nitrogen trihydride, but instead we say ammonia. There are other examples, but that's not why we're here. What I'd like to do is first share my slide set, and we'll run through these rules. Let's see. There's my slide set. And there we go. Okay. So the modern nomenclature for chemistry is rules based. So all you have to do is learn these rules, and this is the beginning. Nomenclature for all chemical compounds is controlled, is generated by this organization. Right? It's the International Union of Pure and Applied Chemists. And they have subcommittees and subcommittees. One of the subcommittees is charged with naming conventions for compounds. And then you subdivide those into the various branches of the sciences. One would be general chemistry, and that's where we're going to start with this system. But eventually you get to other systems, like organic chemistry has another set of rules that are tacked onto these. Biochemistry has its set of rules. So it's all rules based. So the first thing we need to recognize as we start learning how to name compounds is that the convention we're going to use is for what we call binary compounds. Those are composed of two elements, right? Usually elements, but we substitute polyatomic ions for some of these elements, and we'll talk about that in just a few minutes. And you can either name the compound, well, if you understand the compound to be ionic, then it has a set of rules. And if it's covalent, the ionic, of course, will be metal, non-metal. So you would have those two elements combined. The covalent compounds are combinations of non-metal and non-metal. And our discussion of the periodic table showed you where to locate those elements in the periodic table. All right, so the simplest way to understand the rule set is to go by types. So type 1 compounds are ionic. They're metal and non-metal. Okay? That's the first condition. The second condition is that the metal is always a positive ion, a cation. Well, actually, this is corollary to that. And the non-metal is an anion. It's negatively charged. The other main rule for this is that these metals are only the ones that have a fixed charge. In other words, when they lose electrons, they lose 1, 2, 3, however many, and they only lose that many in this type of compound. And there are certain groups and individual elements in the periodic table that satisfy that condition. Right? The alkali metals, the first column, are always +1. Alkaline earths, the second column, always +2. Then we jump across the transition metals to the next part of the representative elements, and we have boron, aluminum, gallium, and indium. Those are +3. Then there are 3 metals in the transition metals that are fixed charge, and that is a silver with a +1 charge, cadmium with a 2+ charge, and zinc with a 2+ charge. Right. So we have alkali metals like lithium, sodium, potassium. That group, they're always +1. The next group, like magnesium, calcium, barium, that group, they're always +2. And then the boron group, aluminum and gallium and indium, those are always +3. Okay, that's the primary distinguishing factor for type 1 compounds is these metals have fixed charges. Okay. So now that we've established that, how do you put them together? Well, when you write the compound, you just put the cation first, and I'm going to put its charge here so that I can explain it. And then the anion comes second. So if we look at the anions, the halogens, fluorine, chlorine, bromine, iodine, are always -1. So if we put chlorine in here, right, What we want to do is balance the charges because these compounds are always neutral. So 1 plus, 1 minus, that's balanced. If we substituted something else in here, say next door to the halogens are the chalcogens, the oxygen group. They're always 2 minuses. So that means we need 2 sodiums. Right? To write that correctly, balance the charges. The pnictogen group, or the nitrogens, are always 3 minus when they're ionized in these compounds. So let's pick phosphorus. Right? Phosphorus would be 3 minus. That means we need 3 sodiums. Okay? That's how you write the compound. Now we need to name them. So let's go back and let's take this compound, NaCl. The metal, you simply just state the name of the element, sodium. The anion would be chlorine, but we changed the ending from chlorine to chloride. So this name would be sodium chloride. Okay? And that's all we have to say. There are 2 umbrella rules that guide the naming conventions. One is that the name and the compound are unambiguous. That just means that when you see that compound written this way, this is the only possible name. No other name will fit. Or if you see the name, you write the compound and no other form for that compound exists. It's a 1-to-1 relationship. There's no other substitutes. It has to be that way. The other is non-redundant. In other words, you don't chew your cabbage twice. In other words, if you've got a name that works and satisfies the unambiguous condition, then you don't need to add any more information, right? We wouldn't have to say sodium monochloride, right? We wouldn't have to say that, saying that there's only one chlorine, right? That's unnecessary information. That's redundant. We don't want to be redundant. So let's take another example. Let's say we have calcium. All right, let's take the name, calcium oxide. So we have calcium here. We know its charge is going to be 2 plus. Oxygen, right? That's where this comes from. Oxygen has a 2 minus charge. So we only need 1 of each. So CaO is the correct formula for that name. All right. So that's type 1. And the distinguishing character of type 1 is the metals have a fixed charge. Examples, potassium chloride, we have a +1 and a -1. Magnesium bromide, we have a +2 and a -1, so we need 2 bromines to balance the charges. And we did calcium oxide already. Okay, type 2 compounds. Type 2s are also metal and non-metal. And they're cation, anion, just like before. The difference is the metal has a variable charge. In other words, it can be, in that compound, it could be one of several different charges. Now, once the compound is formed, that charge doesn't change. But we have to say exactly what the charge is in the name. So, for example, if I say this one, Fe2O3, Fe is iron. Iron is a transition element, and most of the transition elements, except for those three that I mentioned earlier, most of them have multiple charge possibilities. So in this case, we need to determine what is the charge of iron. We know oxygen is 2 minus, correct? Right? So oxygen is contributing 3 times 2 is 6 minuses. Right? So how do we balance that? Well, we need 6 pluses from the cation, 6 plus. But we've got 2 of them. So what charge is assigned to each one of those ions? 3 plus. Right? 2 times 3 plus is 6 plus. And 2 times 3, 2 minus times 3 is 6 minus. That's a balanced formula. Now we need to name it. So naming, you just say the metal first, iron, and then in parentheses, you designate the charge, which is 3 plus, with Roman numerals. And then we say oxide. That's a type 2 compound. It will always have a designation for the charge of the metal. So let's go back the other direction. Let's say we have, well, we got examples on the next one. Let's say we have lead 4 oxide. Right? There's your lead, Pb, and it has a 4 plus charge. Right? Oxygen always has a 2 minus charge. So how do we balance that? We've only got one lead with the 4 pluses, and we need 4 minuses from oxygen to balance. So we need 2 of them. PbO2 is the correct formula for lead 4 oxide. All right. And let's see. I'm going to come back to these in a minute. Polyatomic ions. Let's go to type 3s and get that out of the way. Type 3 compounds. Okay, let's move this down here and put type 3s up here. And these are binary compounds. Type 1, type 2, type 3 binaries. This is always a non and a non-metal. Okay? The thing about nonmetals is they form covalent bonding. They don't form ions. So what we're going to do is borrow some of the convention from the type 1 and 2 and apply it to the type 3 with modifications that are necessary because there are no ions. We simply have to say how many of each atom is in the formula. So let's take an example. Well, first thing you have to do is you have to learn the prefixes. Yeah, these are Greek prefixes. The Greek prefixes here for 1 through 10 are given there. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Those are the 10 that we normally use. They go beyond that, but this is as far as we're going to go today. So if we have, say we have this compound. Say, does that satisfy the first condition for type 3? Non-metal, non-metal. Yes, it does. Then we say how many of each one is in the formula. So we would say di nitrogen mono or monoxide. Chemists have sensitive ears too. Monoxide just doesn't sound right. So we drop one of the O's and just say monoxide. So dinitrogen monoxide is N2O. That's laughing gas, right? The old nomenclature called it nitrous oxide. And some people still use that name. But that's what we call, that would be considered a trivial name. These are systematic names. All right. So let's try one. Let's say we have, how about this one? Diphosphorus pentoxide. Okay. We know we have phosphorus. We know we have oxygen. And we know how many. 2 phosphorus and 5 oxygen. That's the formula. And here are some other examples. Everybody's familiar with carbon dioxide. That's supposed to be the evil compound in our environment. Carbon dioxide. Well, don't say that to a green plant. Carbon dioxide to a green plant is food. Okay, so now let's go back to polyatomic ions. Sometimes we can substitute a polyatomic ion for one of these elements. Now, polyatomic ions are just that. There's more than one poly, more than one atom in the ion. The ion behaves as a separate unit. And this listing gives you the most commonly used. The list on the left is a duplicate of the one on the right, only they're sorted differently. The one sorted on the left is sorted by name. So acetate comes first and thiosulfate comes last. And the ones on the right are sorted by formula. So arsenate comes first and sulfate comes last. I give this list to my students, my chemistry students, because I haven't had one yet that's going to be a chemistry major. So there's no need for them to memorize these. I give them this list so that they can look up the various polyatomics. One characteristic of this list is all of the polyatomics are negatively charged, except for one in this list. And that one is, that's ammonium. Right? So, where would ammonium be substituted in a binary formula? It would be substituted for the metal, the cation. Right? It would go into this position. So, if we have a compound that has ammonium in it, it would always be a type 1 compound because this charge does not change ever. If you change that charge, you don't have the same ion anymore. So this would fit in here. And we could add something else. We could do this. We could say NH4Cl, 1 plus, 1 minus. That would be ammonium chloride. Okay? So it's just a matter of substituting these polyatomic ions where they're supposed to be. The rest of them would be substituted into the anion position. So they could be either this side or this side. It's not likely that you will encounter many of these in your TEAS examination, but I just want you to be aware of the fact that this is a possibility uh, based upon the naming conventions. All right, so those type 1, type 2, type 3 compounds. Now, there's another naming convention that was inherited from medieval times, and we had to sort of grandfather it in to our naming convention. And that has to do with, and this is a flow chart for, maybe we better cover that first. So if you're confronted with a name or a compound, how do you know which one to use? First, you say, is it a binary? Does it have two parts? And then you see, is there a metal present? If there's a metal present in the first position, obviously, it'll either be a type 1 or a type 2. It won't be a type 3 because type 3s are non-metal. If it's a metal, if it's a non-metal, then you go straight to this convention. If it's a metal, non-metal, then you have to decide, is the metal fixed charge or variable charge? And then you decide which one you go to. All right. This convention I was mentioning earlier is the naming convention for acids. So let's go to acids, naming convention. The first condition for an acid is the molecule has to have a hydrogen in its first position. So we would have HCl. So it has that hydrogen because acids are proton donors. If this hydrogen separates from that molecule, it's always a positive. Right? And that leaves behind the electrons that were attached to that hydrogen or that were in the bond here. So what is a hydrogen plus one ion? It's a proton. Well, most of them are protons. Right? It just has one proton and no electrons. So that's why I say it's a proton donor. It provides that proton into aqueous solution to generate acid conditions. Okay. So we have other examples, right? You could have two of them, right? So you have two protons available from sulfuric acid. The other condition is when we name the compound, if we're going to use the acid convention, the molecules must be in aqueous solution. They have to be dissolved in water. So this compound would be named hydrogen chloride if it's a gas, right? But if we put it in aqueous solution, now we have to use our naming convention. So what we do is we look for oxygen. Is there oxygen in that molecule? No, there's no oxygen in that molecule. If there is no oxygen, we start the name with hydro. Then we take the second part of the name and ides become ix. So we say hydrochloric and then acid on the end. So this aqueous HCl is hydrochloric acid. These are other examples. Hydrocyanic acid, this is the cyanide ion, and this is the sulfide ion, so it's sulfuric. Now, if you have oxygen present, for instance, if we have this one, and we name that one by our convention, we would say hydrogen nitrate. NO3 is a polyatomic ion. This polyatomic is nitrate. So, since we have oxygen, now we don't say hydro. We just go straight to the polyatomic, and 8 becomes ic. So now, if it's an aqueous solution, we say nitric acid. That's it. SO4 is sulfate. So 8 becomes X, sulfuric. C2H3O2 is a bigger polyatomic ion. That's the acetate ion. So 8 becomes X, acetic acid. 5% acetic acid is vinegar. If we have HNO2, NO2 is nitrite, right? NO3 is nitrate. NO2 would be hydrogen nitrite. And ites become us's. So we would say nitrous acid. If this were aqueous. Okay? And there's your decision tree if you're so inclined to use it. All right. This exercise is just a test to see if you understand how we name and can pick out a mistake. So A, KNO3 is potassium and NO3 is nitrate. So is this a type 1 or a type 2? Because that's a metal. Potassium is a metal. So potassium is a fixed charge. It's a type 1. So all we have to say is potassium nitrate, and we're done. TiO2, titanium, is a transition element. It has multiple possible charges. So what we have to do with that one TiO2 is say, all right, what's the charge on the oxygen? It's always a 2 minus, which means 4 minus total. So this one has to be a 4 plus to balance it. So now that we know what the charge on the titanium is, we can say titanium, wait a minute. Whoa, that one's not right either. TiO2. Right, the second one's not right either. That one's wrong. Titanium with a 2 plus would only have 1 oxygen, right? So that's an error in the slide. It should be titanium 4 oxide. Let me see if that's even possible. Yep. All right, we can have TiO2. So that one should be titanium 4 oxide. And this one is wrong. Actually, okay. Okay, I see what's happened. There's an error in the slide because of the This green box has been moved. It shouldn't be moved. I don't know if I can fix it here. Yeah, there we go. All right, that's the wrong one. Tin hydroxide. Hydroxide is another polyatomic ion, and it's got a 1 minus charge. So 4 minuses balanced by 1 4 plus charge. So tin 4 oxide hydroxide is correct. Titanium 2 oxide is incorrect. Phosphorus and bromine together, that's a type 3 compound. They're both nonmetals. So we just say phosphorus pentabromide. And notice that if you only have one of the first position, you don't say mono. You just leave it off. That's redundant. If you have the name, if you name one element, there's got to be at least one of them. So we just don't say it. And this is chromate is the polyatomic ion here. It has a 2 minus charge, and calcium has a 2 plus charge. This is a type 1 compound. So all we have to say is calcium chromate. We're done. There's one other convention that you may encounter. And this has to do with waters of hydration. There are some compounds, always salts. In other words, a cation and an anion together. These compounds, sometimes when you isolate them in aqueous solution, so they precipitate out, and you filter them, and then you want to dry them down so you don't have any water left. So you put them in your oven at 105 degrees, and the water evaporates. And then you weigh your sample, but you're curious, right? You want to be sure it's dry. So you put it back in the oven at 150 degrees, and you pull it out several hours later, let it cool in a desiccator, and weigh it again. And it weighs less than it did before. So what that tells you is that there is some water left in there, even at 105 degrees. Those are called waters of hydration, and they're characteristic of some compounds. In this example, we have zinc sulfate. Yeah, zinc is one of those that has a fixed charge, 2 plus charge always. So we only have to say zinc sulfate. But if we only dry it at 105 degrees, there are 7 water molecules left behind for each formula unit. Right? And the way we write that is we put a dot in the middle of the line, and we say how many water molecules. So for each one of these formula units, it will have attached to it 7 waters. Now, how do we name that? We use our Greek prefixes again. This would be just like before, zinc sulfate. And then we would say hepta for 7, and hydrate for water. That's the naming convention. There are others. Say we had this one, copper. Let's see. Yeah, let's say copper CuSO4, like that. How would you name that? Well, we know that copper has a variable charge, so we have to determine the charge. Sulfate is a 2 minus charge, so this one has to be a 2 plus. So we would say copper 2 sulfate penta. pentahydrate. All right. And that's the last of our naming conventions. And that's all you're going to need for your TEAS exams.